The fourth of our colligative properties is called osmosis. And if you hear about osmotic pressure, it's the same thing. Osmotic pressure, osmosis, same thing. It's a colligative property. It's a property that affects the solvent. The solutes will act as blocker molecules, essentially, to make some weird things happen to the solvent, which is really crazy. Osmosis and osmotic pressure is super helpful to biochemists, and it is useful in chemistry in general, but biochemists, as we'll see, can really make some serious advantage of osmosis. In addition, osmosis is really helpful when it comes to finding potable water, like water that you can drink. You can actually take seawater and apply osmosis principles to it to get regular drinking water out. We'll talk about that a little bit. Osmosis is quite different in what it does relative to the other ones, but in osmosis, you generally have a solution on one side and a solvent, pure solvent, on the other. And in between them, you have a semi-permeable membrane, and the membrane allows solvent molecules to travel back and forth, but the solute molecules cannot go through the membrane, all right? So on the solution side, you have solute and solvent. And those solute molecules can't go to the solvent side, but the solvent molecules on the solution side can go to the solvent, and the solvent molecules on the solvent side can go to the solution. And what tends to happen is that solvent molecules rush into the solution side. So if you started with, say, 1 molar sodium chloride, you might end up with 0.5 molar sodium chloride because the solvent is rushing to the solute side, and it dilutes your solution. And it's just a wild phenomenon, but this is something that scientists actually see. So those solvent molecules are moving from the solvent to the solution. It tries to make them both the same solution concentration, but it doesn't do that because on solvent you'd have no solute, and the solute can't get through to that side, but at least tries to dilute the solution so it becomes more like water. It's a really wild phenomenon, and we'll talk more about why this happens in a future lecture, but it is something that's observed by scientists, and it's amazing.
When a solution of higher concentration and a solution of lower concentration are separated by a semi-permeable membrane, one through which solvent molecules can pass but through which solute particles cannot, solvent molecules will pass through the membrane from the side containing the more dilute solution to the side containing the more concentrated solution. This process is called osmosis. Solvent molecules actually move through the membrane in both directions, but because the concentration of the solvent is higher on the right, solvent molecules on the right collide with the membrane more frequently than on the left, resulting in a net flow of solvent from right to left.
So in that video, it's like a U-tube, and not the fun YouTube where you can watch cat videos and stuff like that, but a true U-tube. It's a glass tube with that semi-permeable membrane in the bottom. And again, what happens is the solvent goes from either the side of pure solvent or the side that's less concentrated to the side where you have the solute, where it's more concentrated. So you end up seeing then like a higher pressure on the left side than you do the right in this example. And if you can measure that difference between the pure solvent and the solution, that's a millimeters of mercury, which is a pressure. So osmotic pressure is the pressure of the solvent on the solution, which is just totally crazy still when I think about it. On the left-hand side, this little picture, we've got a little sugar solution in that bag, and it allows, again, the water on the outside to move into the sugar solution, and the water on the sugar solution can go through the bag to the other side. But what you see is a net rushing of solvent molecules to the inside of the bag. So you end up measuring then this height right here, and it's the height relative to the baseline of the solvent. But anyway, it's a measurable pressure. It's a millimeters of mercury, all right? And this is what happens when you have osmosis. So it's a pressure. It's a pressure of the solvent, though. It's not a pressure of the gas like we did back in the gas laws, but it's just an amazing phenomena. It's something that can be observed over and over again. It's very cool. Osmotic pressure gets the symbol of Greek pi. Now, pi is confused sometimes with the 3.1416 number that's used in math. And this is a different use of pi. All right, it's not that pi. This is a pressure. So like pressure in the gas laws was given a capital P. Osmotic pressure, the pressure of the solvent, gets this pi value here to represent it. It's a similar kind of idea, if you will. But anyway, pi, the osmotic pressure, is a pressure in atmospheres, and it's equal to ICRT, where I is the Van Hoff factor, which again is only applicable if you have an ionic compound. C is the concentration in moles per liter. We're back to molarity again, the good old king of the concentration units. R is the gas R, 0.082057, which is liters atmospheres per mole Kelvin, and temperature is the Kelvin temperature. And from all this, you can calculate then what the osmotic pressure will be. So on the right-hand side there, you can see in the solution, you have a measurable distance between the pure solvent and the solution. You can turn that millimeters of mercury into atmospheres using 760 millimeters of mercury, stuff like that. Totally amazing.
When a solution and a pure solvent are separated by a semi-permeable membrane, solvent can flow in both directions, but the solute cannot. Here, pure water moves into the solution, working to bring both the solution and pure water to the same concentration. This process, osmosis, continues until the flow of water across the membrane is balanced by the pressure exerted by the water column. A semi-permeable membrane blocks solute molecules, but allows solvent molecules to pass in both directions. The number of solvent molecules moving from the solution side to the pure solvent side is less than the number moving into the solution side, resulting in a net flow into the solution.
The solute molecules don't go through the membrane because they're either hydrated, like the waters go around, which makes them a lot bigger, or sometimes the molecules themselves are just bigger molecules, more atoms, all right? But for all those reasons, that's why they feel that they don't go through the semi-permeable membrane. But at the end of the day, like I showed on the left-hand video, you do have a pretty measurable distance between the solvent and where the solution stops, and it's usually a height. It's measured in millimeters of mercury. Yes, you could use inches, but don't use that in my class. But anyway, millimeters of mercury can be converted into atmospheres, and that's the pi of the osmotic pressure equation. So pi equals ICRT. Pi is the atmospheres, which comes from the measured distance that the solvent actually pushes it up. It's just fantastic to think about. This is an example of how you can use osmosis. It's a molar mass problem. And again, chemists just love finding the molar mass to make sure that their values are good. And earlier I said how the molar mass... And earlier I said how biochemists can use osmosis a lot, and this is how they use it. Small changes to osmotic pressure will create measurable molar mass calculations, and this is how this works out, so let's check it out. But anyway, in this problem we have 35 grams of hemoglobin, which is some big biomolecule, and you're placing it in water. You make a liter of solution, and after it settles, you found that the osmotic pressure pi is measured to be 10 millimeters of mercury at 25 Celsius. You can use this information to calculate the molar mass of the hemoglobin. So again, 10.0 millimeters isn't a huge amount, but it is something that's measurable, and we're going to use that to find the molar mass. So in this kind of a problem, what you have to do, because you're using the R, the gas constant R, you need to have the pressure in atmospheres. So 10 millimeters of mercury divided by 760 gives you 0.0132 atmospheres. That's the osmotic pressure of the solution. From that point, pi equals ICRT. Now I'm ignoring I here because hemoglobin is basically a big organic covalent molecule. Don't need to worry about it. And most of the time that's the case. So if you solve here for the concentration, which is moles per liter, concentration will be pi over RT. So there's R, 0.082057. Want to make sure you use Kelvin temperatures, so 298 Kelvin. And there's our pressure in atmospheres on top. And this comes out to be 5.40 times 10 to the minus 4 molar, which is moles per liter. Well, we have a liter of solution, so that means we have 5.40 times 10 to the minus 4 moles of solute. And 35 grams, the grams of solute, divided by the moles of solute we just calculated, comes up with the amazingly huge 64,800 grams per mole. And these biomolecules a lot of times have molar masses that are just incredibly large like this one. Very normal for this type of field. In my field, molar masses usually go up to about 400 grams per mole, but in biochemistry, these numbers are very common. So just anyway, osmosis and osmotic pressure is a great way to figure out the molar masses of values of like this, which is pretty cool. Osmosis is really important, and I want to talk about some of the uses here real fast. And one of the important parts is in medicine. If ever had an operation, they hook you up to an IV right away, and the IV is not just pure water, which is actually good, as will turn out, because blood cells are like solutions. All right, they have different pieces inside the blood cell, and you want to have just the right amount of osmotic pressure, both outside the blood cell and inside the blood cell, so you don't have the solvent molecules rushing around. So isotonic means that the concentration of the solute and solvent outside the cell are the same as inside the cell. And if you have that, you can see in that first picture right there, then you have just as many solvent molecules, probably water, going out as you have in, and that's good. Your cells are healthy, all is well and stuff, and you're good to go. However, you can have hypertonic, which is the second column, and you can have hypotonic, which is the third column. Now in hypertonic, all right, you have more solvent molecules going from the cell to the outside. So in those cases, you'd have a high concentration outside. The water molecules inside the cell are trying to equilibrate, so they rush out. So your cells shrink, and that's not good. That'll end up in cell problems. Also, you can have those hypotonics. That's if you had pure water that you were putting in instead of some kind of appropriate IV injection. And pure water then will rush inside your cells, make them bigger and bigger and bigger, and finally it's like a balloon, it'll burst and stuff like that, and that's bad news too. So in medicine, people, they have to make sure that all the solutions are isotonic, so it's good for you, and that's important. So yeah, so osmotic pressure is very important to living systems like you and me. Very cool. Water desalination is becoming a really important tool when you live in a city where there's not a lot of fresh water. And at first, this was mostly used in the Middle East, where it's very hot in desert-like conditions, and there wasn't a lot of water. They would take the seawater, and they would essentially pressurize it. And if you pressurize the seawater hard enough, then it forces what normally happens, which is water molecules going from pure solvent to the solution. If you pressurize it, and you can see it's greater than 30 atmospheres often, you can actually force the solvent molecules through the membrane, so you end up with pure water on the other side. So it's a way to desalinate the seawater, and you end up with drinking water. As water becomes more scarce, this is being used more and more. So Los Angeles has a quite active set of water desalination plants as well. And in the picture down there, you can see they got these big long tanks. They pressurize the seawater. Normal drinking water comes out one side, which is great, and then people can use it, et cetera, et cetera. It's not an easy process to set up, and of course it can be expensive. This is called reverse osmosis because you're not allowing what normally happens, which would be the pure water rushing to the solution, i.e. the seawater side. You're reversing the process, and it is not easy to do. You need really high pressures, but of course you need drinking water. Boy, no question about that. So this is something that's become more useful as society advances.